Good afternoon, everyone. My name is Jenny Nesslage. I'm on the faculty at Chesapeake Biological Lab, and I'd like to give you a brief overview of some of the recent work we've been doing, trying to improve growth modeling in the stock assessments for the Gulf of Maine, Georges Bank, and southern New England. I did it, yeah. So I'd like to first acknowledge our funders, National Sea Grant, funded this project. My co-PIs on the project are Mike Wilberg, also at CBL, Burton Shank at the Northeast Fisheries Science Center, and Jeff Kipp at the Commission. But I also, we couldn't have done this work without working very closely with the Commission's Stock Assessment Subcommittee, who provided extensive support and their knowledge, and really were great in integrating us into the 2025 benchmark to get a lot of feedback on our project. And advance that work. I'd also like to acknowledge the generous data providers who provided a lot of tagging data to support this modeling effort. So just to give you a little bit of background as to why we might want to improve growth modeling in the stock assessment. So the stock assessment in the US for both stock units is the model is a statistical catch-at-length model. And so it relies kind of on this engine within the model is stock, season, and sex-specific growth transition matrices that basically describe the probability of population abundance in any given length bin advancing to another length bin in the model. And that is the engine that moves animals through the different length bins in the stock assessment. So we've identified over time a number of research priorities to improve growth in the model. The first is that currently the molt probability and molt increments that are used to generate the growth transition matrices in the assessment are estimated outside of the assessment model. Ideally, best practices are to internally estimate the parameters of the growth along with all the other parameters of the stock assessment so that everything jives with the data. And so that's something that we've been working towards. Also, we have been assuming that growth is constant, and we have seen throughout the talks today that obviously temperature has an effect and several other potential environmental effects might be impacting growth. So that's something we wanted to explore. Also, we note that the molt probabilities currently used in the assessment are estimated from historical data that were largely limited to female samples, and so we wanted to get better information with updated data for both sexes. So the new growth model that we developed is novel in that it's estimating both the growth probability, in other words, did it grow or did it not grow, and the growth increment, if it grew, how much did it grow, simultaneously in the same mark recapture based model. And so one of the things that we wanted to do with this approach was to code it in the same language that we hope that the next stock assessment will be coded in as well, and that's RTMB. So we've currently running this model outside of the stock assessment, but the hope is that with the next benchmark we can integrate it fully into the assessment and have all the parameters estimated simultaneously for the complete package. The model does generate separate, we have separate model runs for each stock and sex, so that we can generate stock and sex specific growth transition matrices that can be set up based on however you want your time step to look. Do you want your growth to be characterized annually or on a season by season basis? You can set up the seasons to be whatever length you want. So it's very flexible. Wherever the stock assessment ends up going with seasonality, we can try and track that and model it as well. We can also incorporate the effect of days at large and growing degree days or some kind of temperature time series on growth probability. And then the other thing, and that's important, you've seen this graph, Moyle and Pivo showed this graph today of temperatures going up, so we think this could be an important impact on growth and could be impacting the stock assessment, but we're currently not taking that into account. The model also corrects for two potential sources of bias in the use of tagging data to estimate growth, and I'll talk more about that in a moment. So a little bit about the model structure. It has two subcomponents. The first is a logistic submodel that estimates the probability of growth. Does the animal grow or not? And that has three covariates. One is obviously the tagging size of the carapace at length. at tagging. But then also we have days at large and some measure of temperature or growing degree days. So you can have any or all, obviously you pretty much need carapace length, but you can have carapace length and days at large and or temperature, or all three. The second submodel is a linear submodel that describes growth increment, or how much an animal grows if growth does occur. And that also has three covariates: carapace length at tagging, days at large, and temperature or growing degree days. So we explored different versions of this model. If you look in the appendix on growth and the stock assessment, that one just shows the simplest carapace length covariate model. But the one I'm going to show you today is a preview of our very first attempts at incorporating all three covariates. So I mentioned that there are a couple potential biases when you use market capture tag data to estimate growth. One of them is that we know that when a lobster molts, it can often shed tags, right? And that can lead to estimates of growth that are biased if the animals that have grown have actually shed the tag, but you don't know it, right? And you can't recapture that information. So the model corrects for the observed, it basically corrects the observed growth probabilities by accounting for the differential tag retention rates between lobsters that grow and lobsters that don't grow. And we came up with those tag loss correction rates based on two different studies, one that was published on European lobsters using T-bar tags, and then also some unpublished data that Josh Corleone had provided from New Hampshire Fish and Game. And so we made an assumption that non-grower probability of tag loss for non-growers was about 6%, and the probability of tag loss for growers was about 22%. And then the other thing that we're correcting for in this model, I'm going to call selectivity in air quotes as just kind of a catch-all term. Tracy's laughing because it doesn't mean selectivity like you think in a normal stock assessment. But basically this is a catch-all term for describing how the probability of recapturing a tagged lobster and getting that report back is greater for animals that grow than it is for animals that don't grow, because the lobster fishery operates with gear that is size selective. So an animal that recruits into the size, recruit to the fishery of the gear is going to be more likely to be caught than one that hasn't grown. And so we try to account for that with this model. Then we also got to thinking that there are a couple other reasons why it might be biased, including the fact that if it's an egger, if it's the minimum or max legal size might affect, as well as whether it's V-notched. If a fisherman or a lobsterman's going through and processing a bunch of lobster on deck, they might be like, oh, that's got eggs, I'm just going to throw it over, and not look really carefully to see if it has a tag or not. And so this term selectivity is a catch-all for all those potential biases in the rate at which you might get back a recapture report. So basically the model adjusts the probability of observing a growth increment based on the actual amount of growth, and then we estimate a logistic selectivity function that basically causes lobsters that do grow to be recaptured and reported. Wait, did I say that wrong? Yeah, so, sorry, this is really hard to see. How did I actually describe this? The model adjusts probably, oh yeah, so we have the selectivity function. Why don't I just show you? So basically, we estimate a logistic selectivity function using a binomial GLM that basically says if the animal was recaptured or not. It's based on the carapace length at tagging and the data source, because obviously the different data studies, tagging studies, are conducted in different places and in different ways. And we only used animals that were at large over a very short period of time, so they were unlikely to have molted in that time period. And so we're able to estimate the selectivity, this air quotes selectivity, and then we adjust the probability of observing a given growth increment based on the actual amount that we observed it to have grown and this logistic selectivity curve. So the lobsters that are growing less are going to be recaptured and reported less. So what I'd like to show you today is just one application of this for lobsters in the US. As you know, we have stocks unit and sex-specific growth transition matrices I mentioned before in the stock assessment. And I also mentioned that we can adjust the seasonality, and we've explored 4-quarter based growth models to match the current assessment, but we also did an annual growth time step, and that's the one I'll be showing you right today. So basically, we're assuming one growth pulse that occurs on July 1st, and that mimics the timing of the major molt that occurs in the stock assessment. And then we used a comprehensive set of 12 different regional market capture studies that spanned the late 1960s to 2022. And we selected records in this annual version of the model for which lobsters that were recaptured any time in 1 year based on, they were tagged in 1 year and caught immediately the year after. And then we also explored incorporating temperature in the form of growing degree day time series based on, for Gulf of Maine, Georges Bank, the FVCOM estimates of growing degree days, long time series, and then for Southern New England, we used the Millstone Power Plant Institute data where they had estimated growing degree days as well. So I don't have time to show you all the different versions of the model and the sex and stock specific results, but so I'm going to show you some of the partial effects plots just for the female annual growth model here for Gulf of Maine, Georges Bank. So what I'm showing here is the estimated probability of growing on the left here is a function of carapace length, and then the growth increment. So you can see the probability of growing declines with carapace length, and the growth increment declines a little bit, but is mostly at about 10 millimeters. And this is the partial effects on the probability of growing of days at large. Obviously, the higher probability of growing, the longer it's been at large, and then a slight increase in growth increment with days at large. Growing degree days had a big effect in Gulf of Maine on female growth. You can see the hotter it gets, this is growing degree days scaled to the max, the higher the probability of growing, but the growth increment didn't show as much of an impact. So what we're able to do to try and say, if you want to say, well, how does this compare to the assessment, is we take our growth transition matrices from this alternative model and the ones from the assessment, and we essentially simulate the growth of about 1,000 lobsters under no fishing conditions and run that out over a number of years, and we can then show what the average growth and the uncertainty around that growth might be for both females on the left and males on the right. And you can see that in the Gulf of Maine, Georges Bank stock unit, females' growth estimated by the assessment is faster than the growth estimated from this tagging-based growth model. But for males, it actually overlaps quite similarly, which I thought was very similar to what Heather was showing earlier. Well, I'll just show you as well, because I know some of you are from Southern New England and very interested in Southern New England growth as well. Southern New England is a totally different beast. Estimated growth in Southern New England is much, much faster than Gulf of Maine, Georges Bank. You can see the probability of growing is extremely high at lower carapace lengths, and then declines, and then basically there were very few observations, if at almost none, above 100 millimeters, so there's very little growth estimated there. And the growth increment actually declined with increasing carapace length as well. Interestingly, at least with the incorporation of the Millstone growing degree day time series, we saw really no impact of the growing degree temp covariate in the model. I don't know if that's a function of that particular use of that particular data set, or the fact that we've already reached a thermal tolerance at which they are growing as fast as they possibly can. But that's something that we need to work on. And, oh, I showed you the wrong one. I apologize. Go back. That's days at large, not as much of an impact, but again, very similar with growing degree days. And so here we see that when you compare the assessment with our new alternative growth model, that up to about 100 millimeters, well, maybe 95 millimeters or so, the growth is very, very similar. And then we show an asymptote that the assessment does not. This is problematic, but we also don't have any data to inform growth at those larger carapace lengths. And we are unlikely to get that, I think, anytime soon. So, but the important thing is that when we run this through the actual stock assessment model, it ended up not making much of a difference because we don't see animals at those larger lengths. So the effective area lengths that the assessment covers, we're predicting very similar growth with our alternative growth model as what's currently in the assessment. So in conclusion, I think we were able to provide a proof of concept that it's possible to estimate both molt probability and increment simultaneously in the same model. The results were similar to the growth estimated by the assessment across the common lengths that are observed, with the exception of females in Gulf of Maine, Georges Bank. The model estimates were sensitive to assumed selectivity curves and the time configuration of the model, I think we can provide an option for folks who are interested in modeling growth in lobsters, other lobster populations and species, but also other crustaceans. So if you have tagging data and you're interested in this, we will be posting the code in early 2026 on my GitHub site, so please check it out, and I'd be happy to answer any questions if there is time. Thanks.
We do have time for a few questions.
Hi, thank you. I'm Lydia. I'm in Barney Rochette's lab, and actually that's my hand holding that tag lobster in that photo. Yeah.
Sorry, I didn't give you credit.
No. It was just funny. I was like, I know that photo. But I was curious whether this is incorporated in the model, even when you're looking at the tagging data, whether you have seen any evidence of double molting. So instances, because I know like from that tagging data, I've been going through it, and we have those odd cases where, you know, it's been at large for a year, but I tend to look at it relatively to like where they started, and you're seeing, you know, 30% plus relative change in their growth in that time. And we have seen some like evidence where we get really soft-shelled females in like early May and stuff that seems to suggest that there could be some double molting taking advantage. So I'm just wondering if you're seeing any of that in some of your data set, or how that works into the model.
Yeah. Not my data, but everyone's data who provided, but definitely there's evidence of double molting. There's evidence of, I think, to address how that is treated in the model, we're very specific about how we subset the time frame of the data, so we're trying to only get the first molt. And then the variability in that molt by season will get at the double molt. So that's how that's captured, is in the kind of spread around the mean. And the seasonality and how you define that in the model. So we are able to capture that. It just depends on how you define it and how you specifically subset the data. And that's definitely going on. And the other thing we discovered when we were preparing the data for the assessment was that it looks, when you take a really close look at the raw data, there's a difference in seasonality, particularly for females, when you mentioned that, than what we're currently assuming in the model, in the stock assessment model. So the stock assessment assumes that most of the growth occurs on July 1st, and then there's a double molting period of less growth, but some growth on October 1st. But it seems that females are molting in a different seasonality than males. And so I think one of the things that we talked about was with the next assessment, we might want to re-explore the sex by season specific growth when it happens, and how we might characterize that to better capture some of the seasonal dynamics as well as that double molting. Yeah. Cool. Thank you.
I'm just curious, for the double molts that you have observed, are they lobsters of certain sizes, or is it just kind of anyone?
I didn't look closely at the double molts, so with this type of model, you actually don't want to include the double molt information that's in the tagging databases, because that can lead to a bias. And that Andre Punt published that years ago. That's not anything I came up with, but I did not specifically look at that, but that can be looked at if that's something you're interested in. There's certainly information in there.